Hello, good evening, and good day, everybody. Welcome to the latest episode of the Ask Abhijit show. Today, we discuss science, astrophysics, and all that good stuff. So, before we begin, as always, let me greet you all and see who all is there with us. I can see Crazy Brain, Durga, Nilesh, Scranton Beats, Swapna, Animish, Vaishali, Nilesh, Chaitanya, Aditya, Mangesh, Priyanshi, Anadi, Pankaj, Lakshya, Sudesh, Abhiram, Darshan, Rinjim, Vladimir, Adityanath, Chaitanya, Ambarish, Nishchay, Aditya, Jasmine, Trupti, Vladimir, Saurabh, Pratham, Karthik, Harshada, Swadesh, Rajat, Manish, Husna, Haripriya, Prashant, Ayush, Dev Ji, and lots of other people. Good evening, good day, all of you. Great to have you all with me on this show, this fine day, fine evening. And let us get into the questions, shall we? Let's get right into the questions. All right, what do we have for today? Hmm. Kush says, why is it so hard for ISRO to develop reusable rockets for our missions instead of having to build a new rocket every time? It is a very good question. I'm sure it's not hard for ISRO to develop reusable rockets. Uh, it's just that most likely they have not been this sort of project may not have been sanctioned by the higher ups, by the authorities. See, ISRO is a government organization. It's run by the government. Its funding comes from the government. All the orders, all of that, all the directions come from the government of India. So they do what the government tells them to do, right? Um, so yeah, even I have asked this question: why doesn't ISRO do this? I mean, I'm sure it's not an easy technology to develop, but hey, that's what engineers do. They take up difficult problems and they solve those problems. I even heard that some amateur rocket builder tried this for a few years, and he was able to create a small reusable rocket which would go up, and it was able to land successfully back on Earth. So I'm sure it's not that difficult a problem, especially when you have the kind of funding that ISRO has. Yeah, I know comparing an amateur rocket builder to ISRO is not exactly the correct thing to do, but overall the problem they are solving is the same. So it's about a lack of ambition from whoever is controlling ISRO. Right now, what ISRO is doing, it's developing smaller rockets. What on earth is that for? It'll earn a few $1 million per year for ISRO and for the country, but we need to think bigger. Space exploration is going to increasingly be one of the most important facets of geopolitical advancement in the 21st century. By the end of the 21st century, the two or three nations that will lead the world in space exploration are going to be the two or three nations that lead the world in everything. So it is important that ISRO goes in the right direction. We need to build more powerful rockets. We need to build reusable rockets. I mean, when SpaceX started first trying to develop the technology, people laughed at it. When SpaceX first entered the space launch competition as a space launch company, people laughed at it, right? It was very difficult, but they were able to succeed on extremely small budgets because it's an agile entrepreneurial company. It's run by one guy who has a vision. And the kind of budget they had was way lower than what NASA or Lockheed Martin or whoever else was in the picture earlier. It was way lower than their budgets, and yet they were able to succeed. And when they said that they are trying to develop re reusable rockets, people laughed at them, and yet they succeeded, and now they've gone beyond what anybody could imagine. So I'm sure we know there are excellent engineers and scientists in ISRO, and I'm sure some of them would want to develop such technologies. They need to be empowered. That's what needs to happen. We need to empower our scientists. So this needs to happen at the leadership level. uh, So the government needs to take the initiative. I don't think it's that hard for ISRO to do it. You give them the funding, you give them the go ahead, they can do it in the next 2 3 years, maximum 5 years. I'm sure they can do it. But somebody, I mean, they need to be allowed to do this. That is the problem. In a government organization, everything needs permissions and approvals and all that. And right now, it's clear that they don't have it. Even something like Chandrayaan. I mean, we had Chandrayaan 1 in which year was it? 2008, 9, 10, somewhere there. Then the next Chandrayaan mission, Chandrayaan 2, happened in 2019. It was a partial success, partial failure. I was hoping that within 6 months to 12 months they would do the next attempt, and yet here we are, and we're still waiting for that to happen. It's I don't know if it's going to happen this year or not. So it's disappointing, the slow, incredibly slow bureaucratic governmental pace at which things are progressing. Other nations are forging ahead. The Chinese are significantly ahead of India right now. The Americans are anyway the leaders. The Russians have very, very good technology, space exploration technology. The Japanese are doing well. Yeah, SpaceX, a private company, is ahead of ISRO, way ahead of ISRO. Now they are developing the world's most powerful rocket ever, a private company. Yeah, and you have other private companies as well, like Blue Origin, that are already doing the same, right? They also have reusable rockets that can land back on the earth instead of having to dump them in the ocean. So everyone's going far ahead, and ISRO is just crawling because the leadership doesn't have the ambition, as far as I can see. So that is disappointing. I don't think it's hard for ISRO to do this. You give them the right amount of funding, you give them the go ahead, they can do it. The next 2 to 3 years, I'm sure they can do it. Maximum 5 years, maximum. Reusable rockets and much more. They already have the know-how to build much more powerful rockets. The technology already exists. They just need to be able to test it out a few times. So it's just a question of government approval, and that's unfortunately what's not happening, as far as I can see. I mean, obviously, I am not privy to what's going on behind the scenes, the decision making, and whatever else. But as an outsider, from what I observe, it looks like there is these problems are hampering ISRO and slowing things down. So it's frustrating, it's disappointing, but that's where we are. I hope that things change. We have the potential to become one of the top spacefaring nations in the world. Why not do it? It doesn't cost that much of money. So I hope things change. Yeah, because we have the ability and the potential to be in the top 2 or top 3 for sure. Right. Next question. Nikhil says, recently I have read somewhere that a photo of a UFO spotted in Scotland during the 1990s was found, and also read that the particular photo was lost in the last 30 years and now it has been unveiled. How much truth is this, and what's your opinion about this? Okay, let's take a look at the photograph. I think it's called the Calvin photograph, right? Let me see. Let me Google that. Calvin photograph. And let us put that on the screen. What does this UFO picture look like? What does Google tell us? Let's see. Let's go to images. And apparently, this is the best picture that we have of UFOs thus far. This gentleman is holding up the picture. And if you want the details of the picture, it looks something like this. So, this apparently is the best UFO picture that we have that has ever been taken. It happened in this place called Calvin in Scotland, north of Edinburgh and Glasgow. And somebody took this image. So, you have what appears to be an unidentified flying object, a UFO. In the background, you have hills, and you also have an aircraft flying in the background. So it looks like the UFO it appears to be between the observer, the photographer, and the aircraft. The aircraft seems to be somewhat further away than this object, the flying object, the UFO. Is this also that? I'm not sure. So there seem to be multiple versions of this photograph around, but this is the one I have seen earlier. Yes. Yeah, so this is the photograph that we are referring to, the Calvin photograph. So the question is, so apparently this was taken sometime in the 1990s, maybe in 1990, and it wasn't lost. What I read is that the photograph had been suppressed. So the government, the authorities, or whoever it was, apparently the people, the persons, apparently there were two people, two individuals who took the photograph, and then they submitted it to a newspaper or some media outlet for publication. But instead of publishing it, this newspaper or whoever, magazine or whatever it was, they alerted the authorities. The authorities apparently confiscated the picture and it was suppressed for the longest time. So that is what I hear. And that seems to indicate that this is something genuine, something explosive, something that the public should not have been allowed to see, or something like that. That's the kind of impression that this story gives us. So, and now for some reason they have unveiled it, revealed it, or allowed it to be published. And apparently those two people who took the photograph, their identities are still not revealed, and they will be kept secret for the next, I don't know, 2 3 decades, maybe 5 decades. I'm not sure what the time period is, but their identities are have been suppressed. They've been concealed. I don't know why it is so. Maybe to keep up the appearance that this is something very secretive and something very confidential or whatever. I'm not sure what it is. So, what is my opinion about this? My opinion about this is that I am very skeptical about this. This one picture proves nothing. So I read that the experts have said that this is the most authentic looking picture, and it doesn't look like it's been photoshopped or manipulated or anything. It appears to be the genuine thing. But look, I am no expert in photography, and what I see over here, while it's certainly not very grainy, it is a better resolution picture than what you typically get from you about UFOs. Yeah, and yet it doesn't tell me much. I can't really I can't really make a judgment as to whether it's genuine or not. It looks like a craft that could be hovering in the air, but I beyond that I don't know. See, this is not really clinching evidence of UFOs. This is not clinching evidence, in my opinion, of alien visitation to the planet or any such activity. The clinching evidence is if multiple people from multiple angles see the same phenomenon, take pictures or video of it, and it all appears in social media or news everywhere. Why is it always just one picture? Why is it always just one angle? And why does it always happen in English speaking countries? Yeah. So for me, what would represent clinching evidence would be multiple sources photographing or taking video of the same phenomenon, same event. Yeah. Or finding an actual UFO and having journalists visit it, or maybe interviewing an actual alien, something like that, something that is genuine beyond any shadow of a doubt. That is what would convince me. This unfortunately does not convince me. It could be genuine, but it could also be faked. So this does not convince me. I am hopeful, and you know what, I actually am pretty sure that alien civilizations exist beyond our solar system. I'm pretty convinced about that. There are so many stars, galaxies, trillions, gazillions, bazillions of them. Yeah, it's almost a mathematical certainty. It's almost a statistical certainty that there is life beyond our planet. Maybe even in our old solar system, microbial life or so, and there could be intelligent life elsewhere. I'm pretty certain it should be almost a certainty. Yeah, but thus far I have seen no actual clinching evidence that convinces me. I am a skeptical person. That's what I am by training, and by that's just the way I am. Yeah, it's not. I'm not easy to convince. So I am not convinced by what I see. It's interesting, and yet it looks like they're drip feeding one thing at a time. A couple of years ago, the US government got involved in this, started taking UFOs seriously, apparently. In the 1960s, 70s, 80s, they used to put people in mental asylums for saying that they had been abducted by aliens or they had seen UFOs. People were scared to speak about this. And now it's the opposite thing. Now they're taking it seriously and they're announcing various investigations into the UFO phenomenon. They are calling it UAPs or whatever they're calling it now. They're rebranding it. Yeah. And these things only appear in the English speaking world, only mostly in the North American region. So it looks like it's all fabricated to me. This it looks very fishy. I'm not convinced. I get the feeling that they are trying to create this new trend to divert attention from something else. Maybe I'm not sure what it is. Yeah. So my take is very simple. I am not convinced. This does not convince me. There you are. Sorry. Okay, Vinay Man says, "What's your take on the 2,400, no, 24,000-year-old zombie viruses revived and cloned in the Arctic permafrost? What do we mean by the Arctic permafrost? Shall we see what that is? We need to see a map because maps are important, right? We need to see the map. So where is the map? Here's the map. Here's the map. Come on, up here. Here we are. So let's take a look at the satellite image. What's it look like? So if you go far north, yeah, if you go far north, you will see snow and ice. Yeah. So these are the Arctic regions of our planet near the North Pole. Um, and these regions are essentially permanently under snow. For some reason, it's not showing me snow right now here. Maybe global warming has gone too far. I'm not sure what it is. They should all be covered in snow and frost, but here we are. We have some of that here. This is some Zemlia. This is Novaya Zemlia. It's where the Tsar Bomba was tested. So, in the Arctic regions, what we find is that above a certain latitude, the ground is permanently frozen. Permanently frozen. And it's been this way for thousands of years. Now, the thing is this: you've had animals roaming around these places for tens of thousands of years, mammoths, ancient wolves, ancient various other animals, bird species and other species of animals, maybe human beings. And you would also have ancient microorganisms, and these animals would have lived there and died there. And if such animals died in these regions, they would be frozen, and they would be buried under snow over thousands of years. Yeah, that's what would happen. So above a certain latitude, the ground is permanently frozen, and that is what we call permafrost. So it's entirely possible. And we discover mammoths and other animals, ancient horses, etc., very well preserved, very nicely frozen, etc. We discover these animals in these regions from time to time. Every year we get some news of some new animal being discovered, yeah? Right? By various explorers and all that, researchers, etc. But now, because of global warming, some of this permafrost is thawing. It is slowly becoming unfrozen. And when something unfreezes, things that have been frozen, especially microorganisms, they can come back to life. When it comes to animals, if you freeze them, they die. And if you unfreeze them, if you thaw them, they cannot come back to life. In the case of microorganisms, that's not always the case. In the case of plants and their seeds, again, that's not the case. A frozen seed can sometimes be sprouted after thousands of years. I mean, I think some such experiment was actually conducted. So, the issue is this: ancient microorganisms could come back to life as the permafrost starts thawing because of global warming. Now, climate change is a natural thing, it's also a man made thing. There are these cycles of climate change. There are ice ages, there are warmer times. There is a cycle. It's called the Milkanovich cycles, 100,000 or so years. You have ice ages, then you have a time in which there is the greenhouse effect, which warms up the planet. Then again, you have ice ages, and so on and so forth. So that's a natural cycle. But now we are contributing something because of the amount of carbon we are emitting into the atmosphere that's contributing to the warming up of the planet and the atmosphere. So, because of this global warming, which has a natural component and also a man made component, the permafrost is slowly thawing in the Arctic regions. Yeah. And because of that, ancient viruses and ancient bacteria may come back to life. And that is what Vinay is referring to as zombie viruses. I'm not sure why the number 24,000 years is given. It could be 50,000. It could be 10,000. We don't know. So, yeah, this could happen. Ancient bacteria, ancient diseases could emerge again. Maybe you had some animal that died of ancient disease that is no longer prevalent, but now if it emerges again from the permafrost and thaws, then those bacteria may again be reactivated, and they could infect other animals possibly, or even humans if they come across the dead body of the animal. So these scenarios are very plausible now. As the permafrost thaws, these scenarios are plausible. So I don't know what you mean by reviving and cloning. No one's cloning anything. It's just that these frozen microorganisms may unfreeze, they may thaw, and they may become active again. So there is no cloning business happening there, no cloning phenomenon. It's just a reactivation and reviving of ancient microorganisms. Here's the thing: microorganisms are very hard to kill. People have drilled deep below the Earth's surface to layers of sediments that are millions of years old, which would have been exposed on the surface of the planet millions of years ago. And even when they drill deep into the bedrock of the Earth at a depth of millions of years, they are still able to find bacteria there. Bacteria that have been encased in the rock for millions of years. Bacteria that were dormant, almost dead, but not quite dead. So bacteria are capable of becoming dormant for incredible long amounts of time, millions of years. And that is scary. So a few thousand years in the permafrost, 10,000, 20,000, 50,000 is nothing for them. So we could see these scenarios becoming true, and that is scary because we don't know what diseases existed in the past, in the distant past. We don't know what bacteria may have been around, and if they are revived, and if our species Homo sapiens has never been exposed to that, that could be problematic. It would mean that we don't have immunity to that. Typically, we develop a certain amount of natural immunity to most diseases because our ancestors came in contact with those diseases again and again for tens of thousands of years. Some of them may have died, some of them may have survived, and if you survive, you develop some kind of, your body develops some sort of understanding at the cellular level of that disease, and sometimes that gets passed on over the generations. So if such bacteria species are there which we have never encountered before, that could be very dangerous for us. So yeah, this scenario is possible, it is plausible, and I hope it doesn't happen, but we should be prepared for it. Swapnil says, what gives the different metals their individual colors, such as gold, yellow, copper, brown, aluminum gray, among others? Are they naturally found in these colors in the respective ores, or are they artificially coated? There is no artificial coating. You take a piece of gold, let's say hypothetically gold, if you are so rich, yeah? Let's say you are extremely rich, you have a brick of gold, and you take a saw and you slice it. So if you slice it, it will be in two pieces, and still the sliced part which you cut open, that will be the same color. So there's no coating. It's actually that color. And the same goes for other metals. Yeah. So where does this color come from? Yeah. Why is this shirt the color it is? Why is the background in these colors? Why is it so? It's not only about metals, it's about everything. Why is this black? So color that we perceive different colors. What are these colors? Color is an illusion. Color is simply an illusion. You take a metal and you see it through a microscope. You will see the surfaces enlarge, but you can't see the atoms and molecules. But if you take an electron microscope and you go deeper and deeper inside, you will start seeing eventually individual molecules and individual atoms. And you will not see them in any color because atoms don't have color. Color has no meaning at the quantum level, at the at the atomic and subatomic level. So what is color? Color is simply electromagnetic radiation of various wavelengths of frequencies. So if my shirt is blue, it means that it's absorbing red and green frequencies of light, and it's emitting, it's reflecting the blue frequency, and it's absorbing everything else. This black microphone, the fact that it is black indicates that it's absorbing light in all the different wavelengths. It's emitting almost nothing back. That's why it looks black. My background over here is reddish, which means that it's absorbing everything except for brownish reddish wavelengths of light. So that is what creates the illusion of color. In reality, color is just wavelengths of electromagnetic radiation of photons of various wavelengths, and our mind interprets these different wavelengths or frequencies as various colors. It color codes electromagnetic radiation. In reality, there is no color. It's just something that our mind creates to help us make sense of the universe. Because if you had to actually see individual frequencies, it would be too much information for you to process in real time. So what the our senses do is that they simplify the universe for us and give us a dumbed down picture so that we can, well, make sense of it in real time. If there is too much information to process, then we cannot function properly. Yeah. So what gives metals their individual colors is that every single metal absorbs electromagnetic radiation of certain frequencies, and it reflects certain frequencies of light. And those frequencies end up telling us what the colors are, right? So when it comes to gold, it absorbs all the frequencies except for the yellowish and golden yellowish frequencies. So those yellowish wavelengths of light are reflected back, and that's why we see that sort of that color of light coming back at us, and that's why we feel that gold is yellow. Yeah, that's how it is. So that is how it works. That's the simplest explanation I can give you. Astra says, why are Indians shorter in height? Is it because of British colonization for 200 years? I am 5.6 inches exactly father's height and about to turn 17 in October. Can I grow taller apart from genetics perspective? Why are Indians shorter in height? Have you seen me? I know I sit over here, so you can't see my exact size, but I'm not exactly short in height, and I'm Indian. But yeah, if you look at the average demographic statistical thing, Indians seem to be currently somewhat shorter than people from, let's say, the Netherlands or Europe. So certain European nations, Indians on average, I believe, are taller than the Chinese and Eastern Asian people or whatever. Yeah. So why is it so? Is it because of British colonization? There are multiple factors when it comes to your height. If you look at historical data, they found, archaeologists discovered a bunch of skeletons. I believe in the Ganga Valley, skeletons that date back to the deep Stone Age, around 30,000 years before today. And the average height of the skeletons, Indian skeletons obviously, was about 5'11" or 6 feet. So your ancestors were ridiculously tall. The average height was about 6 feet, almost. Yeah. So it's not always been this way. So why is it so? So the truth is, in the past 200, 300 years, India's GDP dropped dramatically, right? India became a ridiculously impoverished nation. Every year there were famines created, artificial famines created by the British based on the Irish model. They had created this artificial famine in Ireland, and they liked what they saw, so they recreated that in India year after year after year, so that Indians could not fight back and could not resist British occupation of India. So when you go through 200, 300 years of near starvation, your food habits change, your body tries to conserve as much energy as possible, and that's why it tends to give you shorter people. Yeah. And because of these 200-300 years of extreme deprivation, of privations, of starvation, the food habits of Indians also changed and they became very frugal. So even today I see people eat very less, and the food habits are not great. There is very little protein that people eat. I'm not saying you should eat meat. There are plenty of protein sources even for vegetarians. So it's up to you. I mean, if you want to eat meat, you eat meat. The thing is this: The food habits changed in the past 300 years, and the effects of the famines obviously did contribute. So that is the reason why Indians are right now shorter in height. Even after 1947 until the 1990s, until the 21st century, India was a very poor nation. India is still a third world nation. As your lifestyle improves, as your diet improves, you're gonna get taller. It will take another 2 3 generations. I can already see younger kids, they're already taller than kids in the previous generations. I can see that. So I think overall, it's because of the effects of the past 300 or so years of foreign occupation and destruction of India. Now your height is 5.6, you're 17. I think typically people keep growing until they are 19 or 20 years old. I think around 19, depending on various factors. So if you want to maximize your potential, see, everybody has a maximum potential height that they can achieve based on genetics. And then whether you achieve that full height or not depends on your lifestyle. Do you eat a good diet or not? Do you sleep enough or not? Do you exercise, or are you physically active or not? If you live a very sedentary lifestyle, no exercise, no running around, no outdoor activity, and if you have a poor diet, you're not going to grow tall. But if you do work out regularly, if you do indulge in athletic activities, if you have a good diet, you will reach your, hopefully, your genetic potential, whatever it is. I don't know what it is. Yeah. So that's what I would say. You want to grow taller, become physically active, go to the gym, lift weights, run every day. Yeah. And eat good food, healthy, balanced diet, lots of vegetables, and a good amount of protein and calcium. Yes. A good balanced diet, and don't eat less. Indians, for some reason, eat very less. I see them eat this much food, like little sparrow. Eat. So that's what I can tell you. I don't know your specific case. I don't know what your genetics are. Everybody has a different set of genes. But yeah, overall, that's the thing. Be physically active, lift weights, run a lot, and eat good food and sleep well. All right, sir. All the best. Karthik says, what is quantum tunneling? How can a particle teleport faster than the speed of light itself? Um, let's talk about quantum tunneling. I don't think I've taken this question before. Interesting, yeah? So quantum tunneling. Okay, let's say I have a ball. Yeah, I've got a tennis ball. I have a wall here. This is the wall. This is my ball. If I throw the ball here, it'll bounce off the wall and it'll go back in this direction, right? It will, every single time. If I throw the ball at a wall, if I throw it at a wall, it will hit the wall and bounce back towards me. That is what we will observe 100 times out of 100, a million times out of a million. The ball hits the wall and comes back. This is what we observe in the real world. But the real world is stranger than what we think. When we go back to the deep, ultra microscopic level, to the atomic and subatomic level of the universe, things are very different. At the quantum level, if you have a quantum wall and you shoot a particle at it, there is a finite non-zero probability that the particle may end up on the other side of the wall, on the other side of the barrier. We call it a potential barrier. So this is a problem that you learn in your ABC level quantum mechanics. One dimensional potential barrier. Yeah. So a potential barrier is like a wall, and you have a particle coming in from one direction, and you have to calculate the probabilities. You do solve the one dimensional time dependent Schrodinger equation. Yeah. And see what are the probabilities of the wave function being on this side of the wall and that side of the wall. And you find that the probability of the particle being on the other side of the wall is non-zero. It is lower than being on this side, but it is non-zero. So that is quantum tunneling. Sometimes in quantum mechanics, a particle can go through a wall, right through a wall. Yeah. Which we can't do in the real world. I mean, in the macroscopic world. So that is quantum tunneling. And it's not just some illusory effect. It actually happens. It actually happens. We have quantum tunneling diodes. We have what is it, the scanning tunneling electron microscope that uses this effect, the quantum tunneling effect. Even when it comes to black holes, Hawking radiation can be calculated as a tunneling effect, quantum tunneling effect. Yeah. So it actually happens. So in the quantum world, at the ultra microscopic subatomic level, particles can actually go through walls. So that in brief, roughly, is what quantum tunneling is. The quantum world is incredibly strange, bizarre. It doesn't make any sense. What happens in the quantum world doesn't make any sense intuitively to us, which is why quantum mechanics, when you first come across it, is quite a shock, especially if you're used to the uh, classical physics. All right. So that is what quantum tunneling is. To understand it simply, it's essentially quantum particles, electron or proton or whatever, going through an actual wall, right through it, like a ghost. So that can happen. So that is what quantum tunneling is. Lakshay says the rate of a formation of stars in a galaxy depends on which factors? Right, the rate of formation of stars in a galaxy. It depends on how much molecular hydrogen you have in a certain galaxy. And not just diffuse molecular hydrogen, but molecular hydrogen clouds. I think they're called molecular clouds or something like that. So, so typically, what you have is, if you see a galaxy, let's take the Milky Way for instance. Most of the Milky Way is empty space, but it's not entirely empty space. It's not a perfect vacuum. You do have a diffuse, very, very, very diffuse gas in this vacuum, and most of it is just hydrogen, but it is not molecular hydrogen, it is ionized hydrogen. What is ionized hydrogen? It's when you strip away the electron from an atom. So when you ionize an atom, it means you've stripped away one or more electrons. And in the case of the hydrogen atom, you just have one electron. It's a proton surrounded by one electron. So you strip away that one electron, you're left with a hydrogen nucleus, which is nothing but a proton. So typically in outer space, in interstellar space, you got this very diffuse gaseous medium, which is protons and electrons. Essentially, that's what it is. Ionized hydrogen. Now, when you have a gas of ionized hydrogen, that cannot cause star formation. For star formation to happen, you need molecular hydrogen, hydrogen molecules, which is essentially atoms, but a molecular cloud. And these clouds need to be cold, not hot. If it's a hot cloud, it will have this outward push, which will prevent uh, the gravitational accumulation from happening and all that. So you need molecular clouds with dust and which are cool enough. So let me show you what a molecular cloud looks like, since we are talking about this. Molecular cloud, pillars of creation, a very famous picture. Let me show you what it looks like. I am showing you the map for some reason. Let me end that, and let me bring in the molecular clouds that I wish to show you. Here we are. These are called the pillars of creation. These are examples of molecular clouds. So these are essentially stellar nurseries. These are where new stars, baby stars are born. And if you look at this image, these are like three fingers. Each of these three fingers is, if you look at the tips of these fingers, even the tips of these fingers are larger than the entire solar system that we live in. We think the solar system is huge. It is smaller than the tips of these fingers. So these are examples of molecular clouds. These are star forming regions. This is a zoomed in image of that. And let me show you some other molecular clouds. These are various molecular clouds, and this is where stars are formed. These are stellar nurseries. As you can see some stars being born in here, right? So now, to answer your question, now that you understand what are the conditions you need for star formation, the rate of formation of stars in a galaxy depends on how many molecular clouds you have and whether you have molecular clouds or not. So I think in the Milky Way, the rate of star formation per year must be like 4 or 5 per year, maybe, in the entire Milky Way. We don't have that high a rate of star formation in the Milky Way. In some galaxies and some regions of space, you have lots of stars being born on a continuous basis. So you need these clouds for such a thing to happen. Otherwise, you will not have star formation. All right, sir. Karan says, how do scientists measure the mass of our galaxy as it also contains empty space? Let's talk about how to measure the mass of any galaxy. Let's talk about a galaxy that's far away. Let's say we want to measure the mass of the Andromeda galaxy. It's about what? How far is it? 1.5 million light years away or so? Yep. So, first of all, we have to understand how far it is from us. We have to first understand the distance of the galaxy from us. Now, how do we estimate the distance, that how far a galaxy is from us? So there are certain techniques we use. One of them is the standard candles, the type 1a supernova. We know what is the relation between the luminosity of a type 1a supernova and the distance. So based, and these supernovae happen on a regular basis, right? So from time to time, you will see these standard candles light up in galaxies. So when that happens, you measure the luminosity of the standard candle, the type 1a supernova. How much light are we getting from there? And based on that, we can estimate to a very good approximation what the distance is to the galaxy. So now we know, once we do this, now we know how far this galaxy is from here. We know the distance. To a good approximation, we know the distance. Now, how do we measure the mass of the galaxy? So we see what is the total light output. How much light are we getting in total from the galaxy? That gives us an approximation. We know the distance, how far it is, and now we know how much light is coming out. So based on that, we can do certain calculations and get a good approximate idea of how much visible matter is in the galaxy. So we now have a good idea of totally what is the total number of stars based on the approximate average luminosity of one star and the amount of total luminosity we're getting. We can get a rough approximation of how many stars there are and what is the total visible mass of the galaxy. Then we look at the rate of rotation of the galaxy. How is it rotating? How fast is it rotating? Now galaxies rotate, for us they rotate very slowly. So how do we determine the rotation rate of a galaxy, speed of a galaxy? A galaxy, let's say it's like this, it's like a disk. Yeah, you see the light at one end and you see the light at the other end. Which end is red shifted, which end is blue shifted, and then based on the amount of red shift and blue shift we have, we can measure how fast the galaxy is rotating. And based on how fast the galaxy is rotating, we can plot that on the rotation curves and we can determine how much dark matter is there around the galaxy. We can determine the size of the dark matter halo of the galaxy. So this is a rough idea that I'm giving you of how we do this. Right? So that's how we can determine how far a galaxy is, how much visible matter is inside a galaxy, and how much dark matter it contains. And of course, there are other things we can do. We can see how much gravitational lensing it is producing. That also gives us an idea of how much matter, dark matter, this galaxy contains, apart from the visible matter. And of course, this is something that takes a lot of time. You can't just take a few photographs and get an idea. It takes years to get an approximate idea of how large a galaxy is and how far it is from us. And as the decades go by, we can refine our understanding based on new data that comes in. So astronomy is not something you can do like in a couple of days. It takes years, sometimes decades. You have to look at old data that previous generations of astronomers have compiled, and based on all this data that we have, we can then arrive at a good idea of how far a galaxy is and how much mass it contains. In some cases, some galaxies are really far away and we may not have a very good idea, but some closer galaxies like the Andromeda galaxy and the large and small Magellanic Cloud, etc., we have a very good idea of these parameters. Yeah, so that's how you typically do it when it comes to measuring the mass of a galaxy and how much dark matter it contains and things like that, right? And similarly, for our own galaxy, we can do such things. For our galaxy, it is slightly difficult because we can't see the entire galaxy. But once again, we can do these things. We can see how much luminosity is there, and things like that. And over time, because we have many decades of data, we can do the calculations and approximately understand how much mass our galaxy also contains and how much dark matter it may be there within our galaxy. So that's how it's done. It's not an exact science because there are so many parameters involved and there is so much we can't see, especially when it comes to our galaxy. But over the years, we've been able to do it well. Okay, Mr. Jesus, Mr. Jesus asks me, what exactly is an ice age? We were never taught this concept in our curriculum. Please help. Please explain. An ice age is a periodic phase in the history of our planet in which uh, there is a period of extensive glaciation on the surface of the planet, which means that the there is a it's a time period. Essentially, it's a cyclical process, right? The cycles last millions of years. There are also smaller cycles that last about about 100,000 years, and even within an ice age, you have periods of glaciation and periods when the glaciers retreat. But an ice age, if you look at the entire history of the planet, is a period when the temperatures are on average significantly colder, like 7, 8, 9 degrees on average colder than otherwise. And it's a period when you have extensive glaciation on the planet. Apart from the equator, most of the other regions would be covered under ice or snow, lots of glaciers, and that sort of thing. So typically, it's a period of time when the average temperature is between 7 to 10 roughly degrees lower than when there is not an ice age. All right. So that is essentially what it is, an ice age. So we are currently within an ice age, actually. It may not feel like that, but we are within an extended ice age. Right now, we are not in a period of glaciation. The last glacial maximum happened about 22,000 years before today. So, about 22,000 years before today, we were at the last glacial maximum when the glaciers and the ice coverage on the surface of the planet was at its maximum. Then slowly the glaciers receded, they started melting, the sea levels started rising. Then, about 12,000 years before today, there was this sudden onset of a small period of glaciation. It's called the Younger Dryas, when again the Earth became cold for a couple of thousand years or so, and then we had these melt water pulses, and the temperature started rising again. And right now we are in this period of global warming because of various factors, including human mediated global warming, human contribution to the amount of carbon particles that are in the atmosphere and so on. So that's how it is. But overall, to answer your question, an ice age is a time when the average temperature across the planet is significantly lower than otherwise. And it's a cyclical process. All right. Okay. Swapnil says, what's the inverse square law and how is it related to the concept of gravity? What is the inverse square law? Well, it's a concept in which a property, let's say a force, is proportional to the square of another to the inverse of the square of any other quantity. So let me give you a couple of examples. Yes. So I can give you a couple of examples. One is the Coulomb's law of electrostatics, and one is the gravitational law. So let's put that on the screen. What does it look like? Coulomb's law. Coulomb's law. And let's put that on the screen so that you understand what that means. So what does the equation for Coulomb's law look like? Well, here it is. Let me put a larger. There you are. F equals K Q1 Q2 upon R square. What does that mean? This essentially tells you that the magnitude of the electrostatic force of attraction or repulsion, yeah, between 2 point charges is proportional to, it is directly proportional to the inverse. It's directly proportional to the product of the two charges and inversely proportional to the square of the distance between between the two charges. That's what it is telling you. So K is the constant of proportionality over here. K is the constant of proportionality. So this is the Coulomb law. Now let's take a look at the Newtonian law of gravitation. Newton's law of gravitation. Law of gravitation. Here we are. So once again, you have a very similar thing. F equals G m1 m2 upon r squared, which means that the force is directly proportional to the product of the two masses and inversely proportional to the square of the distance between the two. So 1 upon r squared, this thing, whenever you have it, it's an inverse square law. So this is how it is related to the concept of gravity. This is the Newtonian law, the Newton's law of gravity, and this is a good approximation of how gravity actually works. If you want a better approximation, you will have to take a look at general relativity. So that's what it is, the inverse square law, and how it is related to the concept of gravity. Aditya says, if there are big cats, why are there no big dogs? Yeah, that's an interesting question, right? So we have a whole lot of big cats. We have the regular house cat, you have leopards, you got cheetahs, you got tigers, you got lions, and you got jaguars and various other kinds of big cats. In the past, we had the saber-toothed tigers and various other big cats that have gone extinct. Yeah. So we had that. Why do we not have big dogs? Do we have any? Let me see. What are the canids? CANIDS, canids. Okay, let me put that on the screen. So these creatures are called the canids. You have the dingo, which is the Australian doggy, Australian wild dog, and various other jackal-like animals, foxes, jackals, wolves, various kinds of dogs. You have Indian canids like the dhole dog, which is a red-colored dog, and then you have the Indian jackal, the Indian wolf, the Himalayan wolf, and so much more. But the question is, why don't we have giant, big ones like we have big cats? So the thing is this: there are animals that are closely related to the dog, such as, for instance, let me see. If you want to look at the taxonomy, etc., we will have to go into the details. So we have canids, then we have caniformia. These are various animals that are related to dogs: the bear, the raccoon, the seal, the walrus, and so on. Various kinds of bears, various raccoons, seals, walruses. I would say even porpoises and whales are related to dogs, right? So here are your big dogs. The panda also, right? So the bear, look at the bear's face. What does the bear's face look like? It looks like a dog, right? And even if you see the seals, they have this barking voice. They bark. Seals, at least some seals bark. So these are your big dogs. They don't exactly quite look like dogs in the conventional sense, the way the big cats look like our house cats. But these animals over here are closely related to dogs. They are part of the same evolutionary uh, family branch, yeah, and they all have common ancestors. So you could consider a bear to be a big dog. You could consider a walrus to be a big dog. You could consider a whale to be a distant relative, a kind of water-based big dog. That's how it is. It's once you start observing it from that angle, you will understand. You will realize that there are similarities. Okay, Vine Gaming says, what is apogee and perigee? When you have an orbit, let's say you have the Earth in orbit around the sun. Now, the Earth's orbit around the sun is not a perfectly circular orbit. It's an elliptical orbit. What is an ellipse? It's like a squashed circle. You take a circle and you squash it, you get an ellipse, right? So the Earth goes around the sun in an elliptical orbit. Let's put that also on the screen, shall we? Um, apogee, perigee. So when you have an elliptical orbit, let's put that on the screen so you get an idea. Here we are. So let's take a look at this. Is it this? Okay, this is the Earth Sun system. Yes. So when you have this elliptical orbit, the Earth will have a in the orbit, there will be a point where the Earth comes the closest to the Sun. And on the other end of the orbit, you will have a point where the Earth is the farthest from the Sun. So the apogee is the furthest place from the Sun, and the perigee is the closest place to the Sun. Let's see over here, perigee of the moon. And the Earth Moon system also has the same thing. The moon doesn't go around the Earth in an exactly circular orbit. The moon's orbit around the Earth is also elliptical. So there is a point in this orbit where the moon comes closer to the Earth, and there is a point in the orbit where it is at the furthest. So the furthest point is the apogee, the closest point is the perigee. The same goes for satellites. I mean, if you have a satellite in an elliptical orbit, if it's a polar orbit, it's not the case. There are various kinds of orbits of satellites around the Earth, but that's how it goes. So this is the apogee and the perigee. This diagram, I think it shows you very well. The perigee is the closest point. The apogee is the furthest point in the orbit. And that should explain that, hopefully. Okay, Samarth says, do severe heat waves like the one in Europe affect the functioning of nuclear plants? You see, nuclear plants are built to a very high degree of safety standards. The safety standards have to be very stringent when it comes to nuclear power plants. They have to take every single dangerous scenario into consideration. It doesn't always happen. Sometimes you do have accidents, but typically they take every single scenario into account. What if there is an earthquake? Hmm? If there's an earthquake, will that affect our nuclear power plant? They will have that scenario already factored in when they build the nuclear power plant, and they will have a fail-safe mechanism that if something like this happens, the nuclear reactor can be quickly shut down. Similarly, if there is flooding, for whatever reason, there should be a mechanism that will take care of shutting the nuclear reactor down immediately or as soon as possible. Similarly, there will be various temperatures at which the nuclear power plant operates. And if you see the temperature inside the nuclear reactor, it's incredibly high, right? A nuclear reactor is a very hot thing, and it generates heat, which is generated in a controlled fashion. I think I have a video on this channel in which which is essentially a nuclear physics crash course in which I've explained in detail how nuclear reactors work and more. So if you want to exactly understand how it is, take a look at that video. I think it's called Nuclear Physics Crash Course on this channel. Whenever you get the time, take a look. So nuclear reactors produce heat. That heat is controlled. You have these cadmium rods that you insert into the nuclear reactor to slow down the process and to control the heat. So the more cadmium rods you insert, the cooler the reactor gets. And if you remove some of them, it gets hotter. So that's how you control the nuclear reaction. And that heat is then used to produce steam to drive a turbine, and that's how you generate electricity from a nuclear reactor. That's typically roughly how it happens. So the heat inside a nuclear reactor is incredibly high, and you can control it with cadmium rods typically. So if you have a heat wave outside, it's not going to affect the nuclear reactor. It will have a minimal effect on the reactor. What's a heat wave like? 5 degrees above normal, 10 degrees above normal. If you have typically 30 degrees temperature, in a heat wave you may have 40 degrees temperature or 45 degrees at the extreme level, I would imagine. A 15 degrees rise in the external temperature makes no difference to the running of the nuclear reactor. As long as you have the cadmium control rods and everything else in place, it makes no difference whatsoever. So there is a very high and very stringent set of safety standards that are typically applied to nuclear reactors. They take all these various possibilities and factors into consideration. What can go wrong? Every single thing that can go wrong, they would have factored it in the design and in the construction of the nuclear reactor. And therefore, we should not be worried about this, hopefully. Yeah. So severe heat waves would typically have negligible effect on the functioning of a nuclear reactor, or a power plant. You have nuclear reactors in deserts. I think last week I had shown one somewhere. And in India, you typically have hot temperatures, right? India is a warmer place than, let's say, Europe. So if the average temperature in Europe in a certain region may be 25, in India it may be 30 degrees, or even 30 to 30, 33 degrees. And yet Indian nuclear reactors work just fine. So, so the answer in brief is severe heat waves would have a negligible or minimal effect on the functioning of a nuclear power plant. Manmat Tiwari says mitochondria produces energy in our body through food, which keeps us energetic. What happens to this energy within the human body when a person dies? As energy can neither be created nor destroyed. So, what are mitochondria? The mitochondria are the power plants within our cells. In our bodies, we have cells, yes, and most of these cells contain these small power plants called mitochondria. These mitochondria, they take various chemicals, etc., and they have these not nuclear reactions but chemical reactions going on inside. And these chemical reactions are exothermic reactions. They produce heat, right? So I think research has been done about the temperatures of mitochondria. So the average temperature of the human body is around 36 degrees Celsius, I think, yes. 98 or so degrees Fahrenheit, if I'm not mistaken. But if you take a cell and you go inside the cell and measure the temperature of the mitochondrion, it is, I believe, the average temperature of mitochondria is about 55 degrees centigrade. So they are quite hot, and they generate this heat that we need to stay alive. And that's why our average temperature is about 98 degrees Fahrenheit, 36 or so degrees Celsius, right? Um, so the mitochondria, they don't produce energy. They see, we consume food. We don't consume just about anything. We don't eat. Um, we eat very specific kind of substances, right? We only eat organic material, plants, or whatever protein people eat, meat and all that. Yeah. So we only eat certain kinds of things. Only certain kind of things can be digested. We cannot eat stones. We cannot eat soil. We can't eat wood. Right? We only eat certain kinds of things, and those things they provide us the nutrients we need, and the nutrients the mitochondria need in order to produce this heat. So it is not producing energy. It is doing chemical reactions that are exothermic in nature, and they release heat. So they break down various chemical bonds, and the breaking of those chemical bonds releases this heat radiation, right? So it is not creating energy or producing energy. It is transforming one kind of energy, the potential energy stored inside chemical bonds, into heat energy. It's transforming one kind of energy into a different kind of energy. That is what these chemical reactions do, and that's what mitochondria do to keep us warm and healthy. And this exists in all animals. So every animal, whether you take a rabbit or a cat or a deer or a kangaroo or a snake, they all have a certain temperature. Some animals are cold blooded, like reptiles and all. But let's talk about mammals, warm blooded animals. So every animal has a certain average temperature, it needs to be healthy. And it depends on the mitochondria and the rate at which they do these chemical reactions and all these various factors. So let's say some animal dies. Let's say a poor, unfortunate rabbit dies. Yeah, what happens? All the chemical reactions stop. For the chemical reactions to happen, you need blood circulation. The blood supplies all the cells with oxygen. Without the oxygen, cells die. All the chemical reactions stop. If an animal stops breathing even for 60 seconds or 2 minutes, I think cellular death starts happening. And the cells in the body are in this very delicate state of equilibrium. As long as the blood flows and the oxygen keeps coming in, they keep doing what they're supposed to do, the chemical reactions and all that, and the mitochondria keep on producing energy, other things. The moment the blood flow stops and the cells become deprived of oxygen, within just a few minutes the cells start breaking down. There are various enzymes within the cell that start digesting the cellular tissues, the cell walls and all that. And yeah, that is an irreversible process essentially. You you can't revive a dead animal beyond a few minutes of death. Let's say an animal's heart stops. If you don't revive that animal within 2 3 minutes or maximum 5 minutes, depending on the temperature, you cannot revive the animal after that. That's how it goes. So what happens to this energy? it the energy is transformed. The body starts decomposing very rapidly, and then the chemical reactions of a different kind happen. So the chemical reactions that produce the heat within the mitochondria, they won't happen anymore. But the digestive chemical reactions of the various enzymes breaking down the body and the various tissues, that's what happens. And then that's called the process of decomposition. So the energy doesn't go anywhere. It is just the material is transformed into something else, and it is then, I suppose, reclaimed back into the earth. That's what happens, right? So that is the entire process of what happens when someone dies or some animal dies. Swapnil Mishra says, was it a systematic or human error that caused the demise of the Russian cosmonaut Vladimir Komarov, who hit the Earth with the speed of an asteroid from space and burned to ashes? He did not quite burn to ashes. He was obliterated. So this, I don't remember when this happened. I think it was in the 1960s. So Vladimir Komarov was a Russian cosmonaut. They called them cosmonauts. Uh, I'm not sure if I should put that on the screen. Anyway, I'll not do it. So what happened is that he went up into space, and at that time, the spacecraft that they were planning to send into orbit was not quite well designed. It had flaws, it had defects, and the astronauts knew it. There was another Russian astronaut at the time. His name was Yuri Gagarin. He was a great Russian hero, the first human being to go into space. He was a test pilot. He was a fighter pilot and a test pilot. Typically, astronauts are typically taken from the Air Force. They are usually extremely good pilots, especially test pilots. So that's what Yuri Gagarin was. Possibly Vladimir Komarov, if I'm not mistaken. Maybe not. But so for this mission, it was actually Yuri Gagarin who was supposed to go into space, right? And these guys knew that the spacecraft is defective. It has not, it's not going to function well. And if Yuri Gagarin went to space, there was a high likelihood that he would die. And for that reason, Vladimir Komarov volunteered to go himself instead of Yuri Gagarin. And that's what happened. He went into space. The launch happened fine, and he did a few orbits or whatever. I'm not sure what the exact story is. Apogee, perigee, whatever happened. He did his mission in space, and then it was time to come back to Earth. And what happened is that the parachute failed. So the spacecraft re-enters the atmosphere at a certain angle, and then there is this heat shield that protects the spacecraft from the re-entry temperatures. And after you come down to a certain altitude, the parachute is supposed to open. Typically, it's three large parachutes that break the fall, and eventually you come down slowly and you come back to Earth with a gentle thump. But if the parachute doesn't open, you're going to hit the ground at a very, very high speed. And unfortunately, that's what happened with Vladimir Komarov. The parachute never opened, and he slammed into the earth at an incredible velocity. And yeah, well, you can imagine how he died. I'm sure it was painless. And I hear that there is a recording of the communications, the last communications between Vladimir Komarov and the ground base as this thing was happening. Yeah, I think the recording may be available on YouTube or something like that. I believe the Americans were eavesdropping on what was happening, and maybe they were able to intercept the messaging. So yes, that's the unfortunate story of Vladimir Komarov. It was human error. It was human incompetence that caused his completely pointless and avoidable death. The spacecraft was not designed properly. There were flaws, there were problems, and yet, because of the political pressure, they had to send the spacecraft in space into orbit before it was quite ready. It's a communist nation. It was the dictatorship of the proletariat, so you had to do what the bosses told you, even if it cost you your life. So Vladimir Komarov decided to go himself instead of putting Yuri Gagarin on the line, and that resulted in his death. That is what happened. And yeah, unfortunate and sad story. Okay, Myron says, why do feather and stone drop together from the same height, fall down on the ground at the same time on the moon? They do it on the Earth too, in the right conditions. It's like this. It's just that's just how gravity works. You take two bodies, you drop them towards the planet, towards the ground. They're gonna fall at the same speed. Let's say you have an object that weighs 10 kilograms, and you have a different object that weighs 10 grams. You drop them from the same altitude at the same time, they're gonna both reach the ground at the exact same time. That's just how it works. That is the law of gravity, right? And yet, when you take a stone and you take a feather, you drop the two, the stone hits the ground first. The feather just floats down slowly, 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 slowly. Why is that so? It's because of uh, it's because of the atmospheric drag. We have air around us. The feather has a very small mass, and it's got a very large surface area. And that's why, because of the atmospheric drag, the feather comes down very, very, very slowly. Its journey towards the ground is slowed down by the atmosphere, by the air around us. But if you make a vacuum, let's say you create a vacuum chamber on the Earth, forget about the moon, you can do it on Earth. So you take a big beaker or jar, you take out all the air from it, create a vacuum, and then you drop a stone and a feather at the same time. They're gonna fall down at the exact same time, even on the Earth. And of course, you can do it on the moon if you can reach there. So that's how it works, right? So over here on Earth, it's because the air and the friction of the air that the feather is slowed down, because it's got such a small mass and such a large surface area. That is the reason they fall down at different times. On the moon or in vacuum on Earth, they're gonna hit the ground at the exact same time. Okay, Dr. Nishchay says humans in today's age are very advanced in terms of technology and healthcare, and yet there is no sure shot treatment of myopia and hypermetropia. So, myopia means short sightedness, and hypermetropia means long sightedness. People still need to wear spectacles, and that number is increasing. I sometimes think there is a spectacle company mafia behind all this dependence on wearing glasses. I think they don't want the cure to be developed or to be revealed, as by doing so, they might go out of business. Am I right? What's your opinion about this? I think modern technology and healthcare has progressed a lot, has advanced a lot. But the problem is that it is all used for commercial purposes. What is a good business model? Tell me. To permanently cure someone or to make somebody dependent on your medicines? You're going to make more money if you, instead of permanently curing somebody, necessitate it for them to keep on taking your medicine in order to stay reasonably healthy. But the moment they stop buying your medicines, they're going to fall sick again. That is a much better business model, unfortunately. So it's the commercialization of healthcare that is causing this. It's the capitalistic model, right? Capitalism is about maximizing your profits. It's about growing your company and growing your profits on a quarter upon quarter basis. Yeah, infinite profits on a finite planet. That's destroying the planet, and that's what is causing all these problems. So most of the illnesses and diseases that people have today, most of them are lifestyle diseases. They can be cured simply by changing your lifestyle. There is diabetes, there is obesity, which is all caused by the lack of activity and the kind of diet that you eat, right? And then you have these short-sightedness, long-sightedness that is again caused by reading too much, too close to your face, or staring at screens all day. Yeah, and various other things. There is the, what is it called, hypertension, and so many other lifestyle diseases. They can be cured permanently just by changing your lifestyle, but it's so hard to change your lifestyle. And then you have things like cancer, and various other things. And so they want us to not be permanently cured of anything. Once you have some condition, they want to keep on giving you medicines for the rest of your life in order to keep that condition under check, under control. So the business model is, don't allow anyone to be permanently cured of anything. Make every disease, every illness, every condition chronic, mild but chronic. As long as you take medicines, it's going to be mild, it's going to be a slight inconvenience, but nothing more. You stop taking medicine, you're going to die. So that is the perfect business model that they've found, and that's how it is, especially in the West. You go to the US, they have the most ridiculous uh, costs of healthcare. Everybody needs to buy this incredibly expensive insurance, and every single thing costs so much, right? So that's how it is. It's very unfortunate that healthcare has become a business. It's become completely commercialized. Everything is commercialized, and that's why we have this thing. It's not just a spectacle company mafia. It's a healthcare mafia. And now in India also, we are seeing the same thing. People need to buy expensive insurance, and a simple treatment can cost, I don't know, crores of rupees, destroys entire families and all that. That's how it is. So India is again following the same business model. 20 years ago, it was very different. You could go to a doctor, instead of prescribing medicines, the doctor would give you a small packet with a few pills. You take those pills and you're done. 3 days, 5 days, and you're cured of whatever you were having. But now they will write these prescriptions. You go to the pharmacy, it will cost you thousands of rupees, and it's a rinse and repeat kind of thing. So yes, it's a corporate mafia that does not want people to be cured of anything. Once you are in the hospital, they want to maximize your stay there, and extract as much money out of you as they possibly can, and that's how it is. It's very unfortunate. They take this Hippocratic oath that they will be ethical and they will cure people, but they do the exact opposite. So yes, I agree with you, Dr. Nishchay Gonge. That's how the world has become, and that is very unfortunate. Um, and if I say something against capitalism, it doesn't mean that I am pro communism or pro Marxism or anything like that. But this model, this business model, is just about exploiting people. It's about exploiting 7-8 billion people and making money out of their lives. They want to keep you alive as long as possible, so that they can keep making money out of you as long as you live. And that's why they want to extend your lifespans, right? But they want you to stay alive based on all the pills that they are selling you and whatever else they're selling you. Very unfortunate. Jasmine says, studies have shown that the expansion of universe is accelerating. That does it mean it will forever keep expanding, and all the stars and galaxies and dark spaces will move away from each other, and the whole universe will die a cold death in a few billion years? What does modern physics have to say about it? Well, 13.8 billion years ago, the entire universe was compressed into a single point like zero dimensional space, possibly a singularity. Then you have this expansion that happened. It's called the Big Bang colloquially. Yeah, the expansion happened. It's still happening, And from all the data that we have, it is clear that the expansion of space-time is accelerating. So if we extrapolate this into the future, let's say 1 billion years into the future, 10 billion years, and so on, we will find that eventually, and if we look at the edge of the observable universe, we find that eventually the acceleration of space-time becomes superluminal, which means it exceeds the speed of light, which is allowed. In general relativity, nothing can go faster than the speed of light inside space-time, within space-time. But space-time itself can expand faster than the speed of light. So that's what we're witnessing. So more and more of the universe is going out of our sight, right? It's expanding beyond where we can see. So the observable universe is getting smaller and smaller, actually. And in a few billion years, only the Milky Way galaxy will be visible to us. Everything else would have been expanded, would have gone too far away for us to see. And it will be gone forever. And eventually what will happen, even the Milky Way, the expansion of space-time will even take the stars, it will pull the stars away. And the Milky Way itself will succumb to the expansion of space-time. Eventually, all we will be able to see is our own solar system. And then, if things continue the way they are going, then even the solar system will be pulled apart. Eventually, even atoms and molecules will be pulled apart, and nothing will remain. Nothing will remain. So this is what is called the big rip scenario. Everything is pulled apart. Even atoms and molecules are pulled apart. And at the end, all that is left is darkness and almost absolute zero temperature. So this is one scenario of the ultimate fate of our universe, the big rip, But we're not sure if that's what's going to happen. Perhaps we're in an oscillating universe. The universe expands for some time, and then something makes it contract again. And instead of a big rip, there is a big crunch, and there is the reverse of the Big Bang happens, and then it oscillates again. That's another possibility. I mean, we don't quite know because we don't have sufficient data, and we don't understand the laws of physics that well thus far. We have a very rudimentary understanding of the laws of physics. So yes, that is one possible scenario, the big rip, where everything disappears, even atoms and molecules are torn apart, and nothing is left. The other scenario is something else could happen, and we could have a big crunch, and time could go in reverse, in a sense, possibly. So yeah, it's these scenarios are currently possible, and we don't quite know what is going to be the ultimate fate of our universe. Swapnil again. Interesting question. How does transcranial magnetic stimulation, TMS, or electromagnetic therapy cure extreme clinical depression? So what is this transcranial magnetic stimulation? It's where you create a magnetic field with an electromagnet, and you place it on the surface of the scalp or near the scalp, and you are essentially generating a magnetic field by running an electric current through this device. And this magnetic field induces electric currents inside your brain through the process of induction. And I think this effect goes a few centimeters into the skull, into the brain, and it somehow seems to have some beneficial effect on clinical depression and other things. We are not quite sure of what exactly happens, and people experience different kinds of effects. Some people have twitching of the face, some people have neck pain, some people have nausea, sometimes symptoms are more severe, some people have no symptoms whatsoever, and overall it seems that there is some kind of a beneficial effect for people who are suffering from either clinical depression or tinnitus, the constant ringing that some people have in their ears and so on. So it seems to alleviate some of these symptoms and ameliorate their condition in some cases. Now, people some people have this, but we're not quite sure how it works, because the organ in the human body that is the least understood is the brain. We have these psychiatrists, etc., who say that they are scientists. They're not doing science, they're doing voodoo. They don't know how the brain works. We don't have the least idea of how the brain works, how the mind works, where consciousness comes from. We don't understand these things. And once again, when you're doing this TMS therapy, it's not possible to study the brain waves and see what's happening within the brain, because the electromagnetic field that you're creating and the magnetic field that's going into the brain is going to interfere with the instruments. So we don't know what's happening in there. But yes, it seems to alleviate some symptoms and make people feel better, people who are especially depressed. And in some cases, people who have their eyes closed and they are subjected to TMS, they seem to experience supernatural phenomena, like something else is in the room with them, something that is not quite human. So most people feel good, like it's some benevolent presence, but some people are scared out of their wits when this happens. So yeah, there are these weird phenomena that happen, and we don't quite know what is happening, how does it affect the brain. We know that there is electrical activity in the brain. We know that. uh, the brain is a bunch of nerve tissue, lots, billions, trillions of synapses and nerve connections, right? It's a natural neural network. You have all these electrical signals that are going around all the time, and when you apply a magnetic field to that, it's going to uh, have some effect on the brain, on the electrical signals, and maybe that's what's causing these symptoms. But we don't quite know what's happening. Yeah. So if you ask me how does it cure things, first of all, I'm not sure if it cures everything, and secondly, what is the mechanism? Well, some kind of magnetic mechanism. It's inducing a current in the brain in some way, and if you're inducing a current in the brain, it's going to affect the nervous signals and all that. So that is roughly what's happening, but what are the specific details, we don't quite know, because we don't know the functioning of the brain itself. So yeah, that's what it is. Okay, Sunil Jain says, mm, dear sir, okay, two questions. Please tell me, what is the 3D shape of a black hole? Is it a sphere in shape or what? And secondly, suppose we create a mini black hole in a lab, let's say 1 centimeter in diameter. Then what if I put my finger into it? What will happen? Okay, let's take question number one first. What is the three-dimensional shape of a black hole? So if it is a non-rotating black hole, a Schwarzschild black hole, it's going to be a perfect sphere. All right. If it is not a rotating black hole, so a non-rotating black hole is called a Schwarzschild black hole. That is going to be a perfect sphere. But if your black hole is rotating in this direction or that, in that case, it will not be a perfect sphere. It's going to be a squashed sphere. It's going to be oblate in shape. What does oblate look like? Let us Google that, oblate. What does oblate look like? Let us put that on the screen so that you get a good idea. Right? So this is what an oblate shape looks like. It's a spheroid. There you have it. So when you have a black hole that is rotating, it's going to be, yeah, like the shape of the Earth, slightly squashed sphere. And if it is rotating fast, it's going to be more squashed. If it is rotating slowly, it is going to be less squashed. So that, in short, is what the shape of a black hole is like. Not rotating, it's perfectly spherical. If it is rotating, it's going to be a squashed sphere. It's going to be oblate. Now, second question. Suppose we create a mini black hole in a lab. Let's say it's 1 centimeter in diameter, and I'm going to put my finger into it. What's going to happen? Your black hole is going to grow in size, and you're going to lose a finger. So if you place any massive object, any material into a black hole, the black hole is going to absorb it, and it's going to grow in size. You put your finger in there, you're going to lose your finger. Your finger's never coming out. Yeah, that's what happens. If you put your finger beyond that black hole's event horizon, that is the point of no return. That's a boundary of no return. You go there, it's not coming back. and the black hole will get attached to your finger. It's gonna it's gonna essentially try to suck more in. And since it's a 1 centimeter black hole, if a black hole is 1 centimeter in diameter, it's going to be a massive thing. It's going to be really, really, really massive. You go close enough to it, it's going to suck you entirely into it, and you're going to get spaghettified. Really, really pulled out, spaghettification. So depending on the size and all that, you're going to have different effects. But yeah, it's not a good idea. If you create a black hole in a lab, if you're able to do that, please don't do that. And if you do it, please stay far away, because it's going to suck you right in and you're never coming out. And before you go in there, and while going in there, it's not going to be a pleasant experience for you. All right. So yeah, that's what it is. Abhijit says, humorously, it's said that without engineers, science is just a philosophy. Engineers deal with messy reality of the universe. As per you, what science, engineering, technology, and philosophy? Why is the ultimate degree in something a PhD, a philosophy degree? Science is about studying the universe. It's about studying nature. I mean, you can take a subset of the universe and study that. So biology is a science. It's about applying chemistry to the principles and laws of chemistry to living materials. That's essentially biology. So to do biology well, you have to understand chemistry, and to understand chemistry well, you have to understand physics. To do physics well, you have to understand mathematics, and so on. So science is the study of the universe in its various forms, in various subsets of the universe. Engineering is about taking the understanding of science that we have and applying it into creating things, into creating technology. So engineering is applied science. It's applied physics mostly, but yeah, you have bioengineering and chemical engineering and whatnot. Yeah. So engineering is about applying science into creating things, into building things. And the output is technology. So you create new technology, you develop new technologies through engineering. Rocket scientists are all engineers. They're not really scientists, they're engineers. They understand physics, they understand aerodynamics, they understand the chemistry of various kinds of fuels and all that, and they build rockets. So they build things. So rocket scientists are engineers. So that is science, there is engineering, there is technology. Philosophy is a whole different thing. Philosophy is the study of the universe in a sense, but philosophy is also the study of things like ethics and morality. Ethics and morality and right and wrong and things like that. So philosophy is a whole different thing. Science is a subset of philosophy. In philosophy, you don't have beliefs, you have logic. Philosophy is logical. You take logic out of it, it's no longer philosophy. So you can have things that like ethics and morality, but if you want to do philosophy, you have to do it in a logical fashion. And then there are other things like religion and spirituality and whatnot, which I can't really define properly, because you ask any person, everybody will have a different definition of that. So these are things you can't really define. But philosophy is something that obeys logic. Now, why is the ultimate degree in something a PhD, a philosophy degree? I don't know why it's a philosophy degree. You think I don't think the PhD is the ultimate achievement a person can have. I know lots of PhDs who, well, what can I say about them? See, to acquire a PhD, you need to take up a certain problem, and you to write a thesis. Now, if you look at the quality of various PhD theses, you will see that it's not always the best quality. And just by solving a certain problem or working on a problem for 3 to 5 years, you're not going to master the subject. So having a PhD is no guarantee that a person is a master of his field or her field, right? So why is the ultimate degree in something a PhD, a philosophy degree? It's just tradition. It's something that's come out of the Western education system. There was a time when philosophy was the highest thing before science became a thing in the West. So I think this tradition continued, and that's why we just keep following it blindly. And that's how it is. Yeah. All right. Karthik says, if a tree falls in a forest and no one is around to hear it, does it make a sound? Let me ask an analogous question. When I'm not looking at the moon, does it still exist? Let's say we do an experiment. We instruct every single human being on the earth to simultaneously look down at the floor, at the ground. It means that for a certain period of time, not a single human being is observing or looking at the moon. What does it mean then? Does the moon cease to exist for that period of time? If nobody is observing it, does it still exist? That's the kind of question you're asking. Well, it still exists. Let's say a tree falls in a forest and there is no one to see it or no one to hear it. But let's say I've kept a CCTV camera there. So the event happens, nobody observes it, but the CCTV camera records it. And 3 months later, I can go there, I can open up the camera, take out the SD card or whatever it is, and then see the footage in my laptop. So the event did happen, and I can hear the sound later on, the recorded sound. So that's how it is, sir. If a tree falls in a forest and no one is around to hear it, it still does fall and it still does make a sound. And you can record that and see it 100 years later if you want. Yeah. So yeah, it's a kind of philosophical question you're asking, but that is the answer. It does make a sound, and it does actually happen. So even if there is no observer to observe the event, you can have a recording, and that recording can serve as an observer. But what if you have no recording? Does it really happen? Well, I don't know. See, the entire planet, the entire universe is interconnected and entangled in some way. So I think events do happen. Even if nobody observes them, they do happen. All right. I think that brings us to the end of the questions that I have for today. Now let's take some questions from the live chat. We seem to have ended a little earlier today, and so let's take some questions from the live chat. So Ishan says, maybe if you did not see the recording, until you see the recording, it doesn't make a sound. Well, the recording is of an event that happened in the past. And that recording is available for anyone to see at any point in time. So the sound already happened. It was recorded, it was captured, and it can be played back whenever you want. So that's the thing, right? That's the argument. All right, what do we have? Concept of fish falling from the sky. Interesting question. This phenomenon does happen. It is observed all across the world. It's a very rare phenomenon, but you have reports of this happening all across the world at various points in time. Yeah. Fish falling from the sky, frogs falling from the sky. So how does this happen? There is a phenomenon called a water spout. Let me put that on the screen if there is an image of that available. Water spout. Let's see what a water spout looks like, shall we? This is what a water spout looks like. It's essentially a tornado. You know what a tornado is? The whirling air phenomenon. So when a tornado happens over water, a tornado is a phenomenon that's caused by extreme low pressure, and that's what causes air to swirl, and it sucks things up. If you see a tornado operating on ground, then you will see that it sucks things up. It pulls trees into the air. It pulls buildings into the air, cars into the air. It has the effect of sucking things upwards. Now, if a tornado happens over water, over the ocean, it's going to suck things up. And what's in the ocean? You have fish in the ocean, right? Or in a pond, in a lake, or whatever. So all these wonderful little fish will be sucked upwards. They will go into the air, and eventually what goes up has to come down. So these fish, they go into the air, up into the cloud, and then the cloud moves somewhere else, and somehow it may happen that it falls on the ground. And so people report this phenomenon of fish falling from the sky. It's typically fish that were sucked upwards by a water spout, by a tornado that happened over the ocean or over a lake or a river, and then it deposited the fish on ground. And so people saw fish or frogs or whatever falling from the sky, and they think it's some great omen from the gods, which is not quite the case. All right. All right. What do we have? Aurobindo Seal says, what if somebody dies in outer space? Body cannot decompose, so will the body float in space forever? Let's say you have an astronaut who is wearing a space suit, and for whatever reason, hypothetically, yeah, this hypothetical astronaut dies in space. Let's say, will the body not decompose? It will decompose. The moment blood stops flowing, the cells and the tissues in the body will be starved of oxygen. So the regular normal chemical reactions will immediately end, and then various enzymes will start decomposing the body. They will start breaking down the cellular tissues, the cell walls, and whatnot. And that is the process of decomposition. You also have lots of bacteria in the body, in the gut, in the alimentary canal, in the intestines. Once the body dies, they start eating up the body. So even if somebody dies in outer space, the body will decompose. If you're wearing a spacesuit, it will decompose within the spacesuit. If a person is exposed in outer space, then first of all, the person will die of lack of oxygen, and then the decomposition process will happen anyway. Right? So that's how it goes. I don't know why I'm getting lots of questions about dying and decomposition, but well, that's what it is. Yeah. All right. Let us see something else. Why are questions? I'm not getting questions about democracy and politics. Today is Science Day. Let's talk about science. Where we are, Israel, India. Please, science. Today is science. Let's see if I have some good questions. Shiv Satya says, tell your opinion about the aerial school UFO incident in Africa. What is the aerial school UFO incident? I had heard about a school and kids and UFO. Okay, let's just Google it. Aerial school UFO. Aerial school UFO. What is that? So once again, this is what it is. It is a report by some people, some kids perhaps, who reported seeing something, but once again there is no photograph. I mean, this is just some kind of image that somebody has made up. I will be convinced when I see actual photographic or video evidence, or an actual interview with an alien, or a captured UFO or spacecraft, some concrete evidence. Somebody makes a claim, it doesn't convince me. Sometimes you have mass hallucinations. That phenomenon has been observed in the past. Mass hallucinations. Lots of people believe the same thing. They all hallucinate something together. It's happened. These are various psychological phenomena that happen. So as far as I don't have actual evidence, yeah, I know some kids are talking about it in this video. It still doesn't convince me, unfortunately. I need to see incontrovertible evidence in order to be convinced. And yeah. All right. What else do we have? Who is Virgil Grissom? I regret that I don't know who that is, unfortunately. Maybe I'll try and look it up in the future. Okay. Karan says, what will be the shape of our galaxy when it will merge with Andromeda galaxy in the future? We don't know. There's going to be a nice gravitational dance, tango. The two galaxies will come together. They will pass through each other. Some stars will be flung out in different directions. They'll go far away. Then over time, they'll come back. So it'll be a merger process. Maybe eventually you may have a spiral galaxy, or maybe a spheroid oblate galaxy. We're not quite sure. We would have to do various computer simulations to see what actually happens. I have seen certain videos of computer simulations of galaxies merging. It's a messy process. And eventually you have this spherical or spheroid oblate kind of galaxy that emerges out of it over time, over a few billion years. So maybe that's what happens, but we are not 100% sure because there are so many parameters involved. And so we have two spiral galaxies merging, most likely something that looks oblate or spheroidal, most likely, but we cannot be 100% sure of that. Okay, what else do we have? Mm, is reincarnation a mass halogenation? Look, I think you're trying to say if it is a mass hallucination. Look, I don't know. I have no understanding of reincarnation or supernatural things. Reincarnation is not a scientific thing at all, and it's not a mass thing. So we have these claims that some people make that they can remember a past life. It's not something that multiple people are remembering, right? It's just one person remembering an individual alleged past life. So there's no way of proving it, right? There is no scientific way of correlating one consciousness or one person with somebody who died earlier. There is no actual way to 100% prove that. So yeah, so it's not something that is accepted by science for obvious reasons. All right, where are we? Democracy again. I'm not answering questions about democracy today. All right, what do we have? What are the latest findings of the James Webb Space Telescope? What do you make out of it? I haven't been keeping up with all the latest findings. I think there was a set of images that were released some time ago. I think I had spoken about that. So what we are seeing much better images when it comes to certain galaxies that were seen in the past. We are seeing much sharper images and all that. So it's clear that this telescope is much more superior than the Hubble Space Telescope, and it seems to be discovering a new furthest galaxy ever seen almost every week. So it's still a process that's happening right now. I have not kept up with all the latest news in the past couple of weeks. Maybe I will do it, and maybe I can answer this question in a little more detail maybe next week or so. Yeah, but yeah, it seems to be making new discoveries every week. Every week some new galaxy is discovered that seems to be the furthest or most distant galaxy ever discovered. So yeah, we're just in the beginning phase of this, and it's going to discover a whole lot of stuff that is going to change our understanding of the universe. So yeah, it's very exciting. I'm very happy to see this, very excited to see what else comes in the future. All right, what else do we have? uh what do we have? Let's see something interesting. Does light travel at the same speed in all directions? Yes, it travels at the same speed in all directions in vacuum or in any medium. So if you take glass, for instance, the speed of light in glass is the same in all directions, but it is less than the speed of light in vacuum. So light travels slower through glass than it travels through vacuum. And similarly with water, once again, it travels slower in water than it travels through vacuum, but it travels at the same speed in all directions inside water. Vardhan says, what will happen if all hydrogen on the sun gets used up? Well, it depends. Once you run out of hydrogen, you're going to start fusing helium. Once you run out of helium, you're going to start fusing heavier elements, and every star has a certain limit up to which it can fuse things. If a star is about roughly 20 times the mass of the sun, it can keep fusing heavier and heavier elements until it starts producing iron at the core. And the fusion process that creates iron, it consumes more energy than it releases. and that is going to cause the collapse of that star. And if the star is about 20 times or so the mass of the sun, it's going to eventually collapse, go supernova, and give you a black hole at the center. But in the case of the sun is not a big star. It's a small little star. Yeah, it's not a very particularly large star. So what will happen with the sun is, at the end of all this fusion process, when all the hydrogen is used up, the helium is used up, at the end it's going to stop at carbon. It's not going to be able to fuse or create any elements heavier than carbon. So at the end of its life cycle, it's going to give off the outer layers of its atmosphere, and it's going to be left as a white dwarf. What is a white dwarf? It is an extraordinarily hot carbon nucleus, crystalline carbon nucleus. You know what crystalline carbon is called? It's called diamond. So a white dwarf is an extraordinarily hot, massive diamond. That's what it is. And after many, many billions of years, it's going to cool down and become a black dwarf. That is the ultimate fate of the sun. Right, right. Where else do we have? No, I'm not answering questions about souls. Souls. Hmm. Can there be a possibility of having a human civilization in every galaxy? It may be possible. Human civilization, human like civilization, humanoid beings, it is possible. The probability, I would say, is non zero, but we don't exactly know what it is because we don't have sufficient data. The only data point of life that we have is our planet. So we only have one known data point in the entire observable universe. I would say that the probability will be there. I think life definitely would exist in all galaxies or most galaxies, and even intelligent life. But human civilization, I don't know. Human like possible. But once again, I cannot really answer the question because I don't have enough data. No scientist, nobody can answer the question. I would say, from my gut feeling, it's possible that there will be life in other star systems, other galaxies, maybe even human like life, but we don't know for sure. We will know only when we discover it for the first time. Right. What will happen if the rotation of the earth slows down or increases? If the rotation of the earth slows down, the days will become slower, will become longer. And then obviously that sort of process, if it happens, will take time. And as the days go become longer, the tides will change, the earth moon system will be affected, the circadian cycles of living beings, animals, birds, insects will be affected, and so on. And if the rotation increases for whatever reason, the days will become shorter. Instead of 24 hours, you'll have 22 hours, 19 hours, whatever. In the past, it was like that. The earth's rotation speed was not always the same. In the past, maybe a couple of billion or so years ago, I think the length of a day on earth was about 19 hours, which means the rotation speed was faster, and so on. So it's a process of change. The only thing that remains constant is change itself. And depending on the speed of rotation, the length of the day will change, and life will have to adapt according to that. But obviously, it happens so slowly that life is able to adapt. Right. Okay, Sahil says, aren't hydrogen cars risky as hydrogen is highly combustible? Why is India betting on it rather than lithium batteries? Um, yes, hydrogen is indeed combustible, but if you develop safe technologies, then it will be fine. Even petrol is combustible. Obviously, it's not as combustible or volatile as hydrogen, but hydrogen is something that you can produce cheaply through electrolysis of readily available water, which is available in incredibly abundant quantities. So it makes sense to explore that possibility. Yeah, of course, there is a risk in that. Everything has a certain risk. So you have to mitigate the risk. You have to develop technologies that make it safe to use, right? Lithium batteries destroy the environment. You have to dig the earth. You have to pull lithium out. It produces a huge amount of waste. It's not good for the environment in the long run. That's why hydrogen makes more sense. You don't want to destroy the planet in our quest for batteries, right? So that's why hydrogen is a long-term sustainable solution, much more sustainable than lithium ion batteries. It has this problem, it's highly combustible. So we will have to develop the appropriate technologies to mitigate that problem. But obviously, hydrogen makes much more sense because we are not destroying the planet in order to produce hydrogen. The only waste product that we are producing to produce hydrogen is oxygen, which is not really a bad thing, right? So that is the reason why there is this emphasis, there is this push towards trying to see whether we can use hydrogen and adopt it on a mass scale. Right, what else do we have? Are we done? I think there are lots of questions. Akshay says, why does Mercury, despite being small, have more gravity than the moon? Because it is more massive than the moon. It is small, but it is not as small as the moon. If you see, if Mercury has more gravity than the moon, I as of right now, I don't remember exactly what the mass of Mercury is and what the mass of the moon is. Let's say you have two bodies, body A and body B. If body B has more gravity, it means its mass is greater than body A. It's as simple as that. So in case Mercury has more gravity than the moon, it means it is more massive. It may be small, but the moon is smaller. All right. Right. Okay, let's take one more question. One more question. Is the Earth's weight constant? Overall, the Earth's weight is more or less the same. I am sure that there is a certain rate at which the Earth is very slowly losing a small amount of its atmosphere every second. There's a small rate of change, but that is obviously negligible. So I would say that the weight of the Earth is more or less constant. The solid part of the Earth and the liquid part of the Earth is, I'm sure if you add it all up together, it would be very similar to what it was maybe a billion years or so ago. So for all intents and purposes, the weight of the Earth is indeed constant as far as we are concerned. Obviously, if you take a time period of 4 billion years, the age of the Earth is about roughly 4.5 billion years. In that time, I am sure it's more or less constant. Maybe a little bit of mass may have been lost, maybe through collisions with other solar system objects, uh, comets, asteroids. Maybe there was an ancient collision with another body which gave rise to the moon. So if you disregard that, the mass is more or less constant, right? Okay, I think we are done for today. We are almost at the 2 hour mark. So thank you very much, all of you. Thank you for the great questions. Always great fun talking to you. And I will see you in tomorrow's session in less than 24 hours from now. Until then, take care and good night. Good day.